We're going to do the second half of 5.3 today. And on this section, the second half of 5.3, the first half we had a lot of vocabulary. On this section, we're going to be able to state the end behavior of any polynomial function, all right? Any degree polynomial function. So I have graph paper. Could you guys please just sketch y equals x squared? It's going to be this exact parabola. The vertex is at 0, 0. And then you have the coordinate at 1, 1, at 2, 4, and at 3, 9, which is off. And then map them over to the other side, and you'll have the parabola. You don't have to do this XY table, okay? So hopefully you have that parabola sketched. And now I want to actually talk about end behavior, right? Now, in order to be able to write down the correct end behavior notation, we need to be able to say or understand this. As you go to the left on your x's, are you going up or down on your y's? As you go to the left on your x's, are you going up or down on your y's?
It depends
on this specific graph right here. Up, right? So if you're going to the left on the x's, you're going up on your y's. If you're going to the right on your x's, you're going up on your y's. We understand that, right? I mean, it's just pretty much coordinates like 1, 1, 2, 4. But anyway, we're going to write that as with the correct end behavior notation. Check it out. We're going to write end behavior. Go ahead and jot that down. And end behavior is where the graph ends up at the end, okay? So obviously it ends up here and up here. But we want to write that description of it ending up here and up here with the correct end behavior notation. And we're going to write it like this. This is the first time you see it. As x approaches, you put an arrow representing approaches, positive, or actually let's go with negative first. Negative infinity, as x approaches negative infinity. Now that notation right there is really saying look to the left, okay? As x approaches negative infinity, that's really saying as it's going to the left. Because your x number line, here's 1 for the x, 2 for the x, 3, 4, 5. If you keep going this way, you're going to get to positive infinity. Here's negative 1, negative 2, negative 3, negative 4, negative 5. If you keep going this way, you're going to get to negative infinity on the x. So right here, when it says as x approaches negative infinity, that's really saying look to the left. So as x approaches negative infinity, your y values, but instead of writing y, I want to write f of x. It's the same thing as y. Your y values, your f of x values approach what? Positive infinity on the y's or negative infinity on the y's?
Positive.
That's right. As you go to the negative infinity on the x's, it goes to positive infinity on the y's. So we're going to put positive infinity on that f of x. Make sense? Now let's look at it to the right. Right here it says look at it to the left, right? So as x approaches positive infinity, that's saying look at it to the right. As on your x's, as it goes to the positive infinity this way to the right, where do your y's go? Do they go down or do they go up? They go up. So we're going to say that your y values, your f of x values, go where? Up, which means what? Positive or negative infinity? Positive infinity. Obviously, positive means up, negative means down when you're talking about y values. And that is the correct end behavior for that parent graph parabola that we're all used to from semester 1, y equals x squared. Any questions? If you kind of understand that, that's great. If you don't understand it, that's okay. Because, of course, we need to go through several more to be able to understand this. Now, what if I were to put even before modifying anything, we need to also talk about algebra 1. This is quadrant 1. This is quadrant 2. This is quadrant 3. This is quadrant 4. You guys remember that from algebra 1? Yeah, if you don't, let's understand it now because it's a lot easier for me to ask you, like, where's the end behavior? Where does this parabola end up? Oh, it ends up in quadrant 1 and quadrant 2, right? Now, what if I were to put a negative sign? What if the leading coefficient was negative? What would happen to this parabola? It would open down. So the end behavior would no longer be up here. It would be down here, right? Right here we have y equals negative x squared. Obviously, that negative leading coefficient, instead of having the end behavior up there, it's now down here. And I did forget to put an arrow right here, sorry. But anyway, where's the end behavior at now? It is in quadrants 3 and 4, not in quadrants 1 and 2. And that's because of the a value being negative. Are you with me? Okay. What if this is what I want. This is what I want to do. You could take out Desmos if you want, or you could just follow my picture, because I took a picture of my Desmos screen. You see, I graphed y equals x squared, which is a parabola. And then I graphed y equals x to the 4th, y equals x to the 6th, y equals x to the 8th. And I want you guys to conclude that any function that has an even degree is going to look like, what could we conclude from this? Look, this has all the functions with even degrees. What could we conclude? All even degree functions have the end behavior where? In the first and the second quadrant, in quadrant 1 and quadrant 2. So that's a very, very important part of today's lesson, that if your degree is even and your leading coefficient is positive, then your end behavior will be up here in quadrant 1 and up here in quadrant 2. Yay? Okay. Now, what if your leading coefficient was negative? What would that do? That would cause this thing to flip upside down, and it would be in quadrants 3 and 4, right? Okay. So right here, I did graph y equals x squared, that's a red one. Y equals x to the 4th, that's a green one. Y equals x to the 6th, that's a purple one. Y equals x to the 8th, that's a black one. Any even degree function is going to have the end behavior in quadrant 1 and quadrant 2. Okay. Now, what if I focused in on x to the 4th, which is that green one right there? I really can't tell the difference, but let's say x to the 4th. Now, what if I didn't just put x to the 4th? What if I put y equals x to the 4th plus 2x to the 3rd minus 3x squared minus 2x plus 1? In other words, I put a bunch of other stuff with that x to the 4th. But notice it is in standard form. It does have a constant at the end, right? What would that change? It would just change the middle part of the graph. The end behavior would still be exactly the same, okay? So if I wanted to talk about strictly end behavior of this guy, because it's an even degree function and because the leading coefficient is positive, I know my end behavior will be up here and up there in quadrant 1 and 2. Do you understand? Okay. Let's actually take a look at the graph. And there it is, graphed on Desmos. It has an end behavior up in quadrant 1 and quadrant 2. Cool. Of course, the end behavior is the same, but the middle part, that's where it changes. Like it has some different curves and stuff. So when you start adding other terms to your 4th degree polynomial or your 8th degree polynomial or your 12th degree polynomial, if it's even, it's still going to have end behavior up here, but the middle part changes. There's different curves and stuff. Okay? And today we're only worried about end behavior. So going back to all the even degree functions that are simple, that doesn't have a, like y equals x to the 8th is that black one. Now if I did put y equals x to the 8th plus x to the 7th minus x to the 6th plus 5x to the 4th, then other changes would happen right here in the middle, but the end behavior would still be the same. Even degree functions always have an even amount of arrows either pointing up or pointing down. That's an easy way to remember it. An even degree function always have an even amount of arrows in the end behavior either pointing up or pointing down. Let's take a look at the most basic, or not the most basic, but let's look at an odd degree function. We just talked about even degree functions. Let's look at odd degree functions. Let's go back to our graph paper and let's jot down the function. It's a pretty basic one, straightforward. Y equals x to the 3rd. That's an odd degree function. And I do have an XY table right here. I want you to plug in -2, calculate it, get an answer. -1, calculate it, get an answer. 0, plug in 0, 0 times 0 times 0 is still 0, so that's easy. And 1, plug it in, and 2, plug it in. And then graph it. All right, let's do it together then. If I plug in, let's say 1, that's an easy one. What's 1 times 1 times 1? 1. So when I plug in 1, I get out of 1. Let me actually graph 0, 0. It's right here at the origin. Graph 1, 1. It's right here. Graph, let's plug in 2. 2 right there. 2 times 2 times 2. What's that? 8. Okay, so 2, 8 is a coordinate. So if we go 2 on the x, 8 on the y, we're right here on the edge because this is an 8 by 8 graph. Anyway, so far it kind of looks like a pretty narrow half a parabola, right? But when we go to the negative values, when I plug in -1 right there, what's -1 times -1 times -1? It's actually -1, right? When I go negative 2 times negative 2 times negative 2, negative 8. So I have negative 1, which is right there, and negative 2, negative 8, which is down here, and that makes it not a parabola. That makes it like a snake-like curve, right? Okay. So what about the end behavior of this odd degree function? Where does it end up at? First and third quadrant, right? First and third. Now, let's actually write down the end behavior of this guy with the correct end behavior notation as x approaches, and it depends how you want to look at it. Do you want to look at it to the left or do you want to look at it to the right? Either way, we're going to look at both. You want to do the left first or right first? Right? Okay, so if I want to look at it to the right on the x's, I'm going to say as x approaches positive infinity. Okay. Now, what could he tell me? As x approaches positive infinity, where are my y values going? Are they approaching positive or negative infinity on the y's? Positive infinity. Okay, so I know a couple of us are getting it. Again, this right here means look to the left, right, up, or down. This means to the right. What does this mean? Look left, right, up, or down? Up. Your y value is going positive, that means up, right? If it were your y value is going negative, that'd be looking down, right? So right here it says, as x goes positive, that's saying as you look at it to the right, where are your y's at? They're going up to positive infinity. That's what this says. So now let's look at it to the left. What am I going to write? As x goes to negative infinity, that's looking to the left. What do I write? Your y's, your f of x's, go to negative infinity as well. Cool. That's end behavior notation. That's what we want to get good at today. Okay? So what do you think would happen if I put a negative sign, a leading coefficient that's negative right here? What do you think would happen to the end behavior that is originally up here in quadrant 1 and down here in quadrant 3? What do you think would happen if I put a negative sign right here? The end behavior would flip. It would end up here and down here. Okay? Makes total sense. It's the same thing as a parabola. If you have a negative out there, it opens down instead of up. The end behavior gets flipped to the other side of the x-axis. Okay, so I also went to Desmos and I typed in a bunch of odd degree functions, starting with the easiest, y equals x to the 1. That's just a line, a diagonal line going right through the origin, crossing through what quadrants? What do you guys think? Quadrants 1 and 3, right? But check it out. I did y equals x to the 1, y equals x to the 3rd, y equals x to the 5th, y equals x to the 7th, and all of them end up in quadrants 1 and 3. End behavior is up here, end behavior is down here. That is quadrant 1, that's quadrant 3. Okay? And of course, we could state the end behavior with the correct end behavior notation for any of these odd degree functions. You could say as x approaches positive infinity, y approaches positive infinity. Or I should have said as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x approaches negative infinity, right? Okay, so again, your odd degree functions all end up here and down here, unless you actually get a negative leading coefficient, which would cause it to flip up here and down here. Does that make sense? Okay, cool. Now, it's really hard to tell the difference between which one's which, but like, I believe this was x to the 1, y equals x to the 3rd, x to the 5th. That purple one is x to the 7th, that purple one, x to the 7th, y equals x to the 7th. Now, what if I were to take that y equals x to the 7th and just slap on a bunch of other stuff, but of course, I want to write it in standard form, okay? The end behavior is still going to be the same, okay? Where's it going to end up at? Quadrant 1 and quadrant 3, right? It's going to end up here and down here. But all of this other stuff right here, all this other stuff, all it's going to do is it's going to make some more interesting graphs right here in between the end behavior down here and up there. like it might go something like this, up, down, like that, something like that, right? So it might look like that, but let's actually look at the exact graph on Desmos. There it is. And of course, end behavior down here in quadrant 3, up here in quadrant 1. And of course, look at that more interesting graph. It goes up, it goes flat, it goes up, down, up. So yeah, other things happen when you add on other terms to your 7th degree function. But the end behavior, that's all we care about today. The end behavior will always be the same for any odd degree function. Sound good? Okay, now what if I were to take y equals x to the 7th and put a negative in front of it and add on a bunch of other stuff, standard form? What does this negative do to our end behavior? Where will it end up? Second and fourth. There you go. Second and fourth. So it end up here somewhere and down here somewhere, right? Now, all of this other stuff right here is just going to mean that some other stuff happens in between this end behavior and that end behavior. So it might go down, up, down, like who knows, right? I mean, I do know it's right there. And yeah, like we said, end behavior in quadrant 2 and quadrant 4, but other things happen in the middle. Okay, pretty simple. So I did give you a page of printed notes. This first part was from yesterday, 5.3a. It's just a review, and it's good to think about it because you'll have questions like this on the test. State the leading coefficient of this guy. Anybody? Leading coefficient.
2.
Excellent. 2. You got to think of the highest power first. What do we call this 3? What do we call it?
Degree.
The degree. So if they ask you state the degree is 3. How about the constant? -1. Great. Easy points on next week's test. And here we have part B, which we're talking about end behavior, okay, and the notation. So obviously, this guy right here has an end behavior down here in quadrant 3 and up here in quadrant 1, end behavior quadrant 1 and quadrant 3. Let me ask you this. Do you believe that this is an even degree function or an odd degree function? Even degree function or odd degree function? It's odd for sure. Now, here's a super easy way of identifying whether it's even or odd. How many arrows do you see pointing up? 1. The number 1 is odd, right? If you were to see 2 arrows pointing up, then it'd be an even degree function. Or 2 arrows pointing down, that'd be an even degree function. But if you only see 1 arrow pointing down, that's the number 1 is odd, so this is an odd degree function. Cool? Not only that, you know it's an odd degree function. Do you think that the leading coefficient is positive or negative? If it's down here and up here? Positive, right? If you think about the most basic one, y equals x to the 1, that's odd, right? That's up here and down here, quadrant 1 and quadrant 3. So yeah, we could already tell a bunch of things here, like the leading coefficient is positive, it's an odd degree function. The notation we already know. As x goes to negative infinity, that's saying as you look to the left, the y values go to negative infinity, it goes down. But you know what? There's on the worksheet, there's this like, I don't know why, but the answers sometimes when they ask you for the end behavior notation, they write it backwards for some reason. They write it like this. As f of x approaches negative infinity, your x values approach. Now, what does this mean? As f of x approaches negative infinity, does that mean left, right, up, or down? That means down, right? So, I should say down, correct? Because if I say right, you might think right. So this means down. So if you look at this graph and you're looking at it down, does it exist to the left forever or to the right forever? To the left forever, right? So as f of x is going to negative infinity, your x is also going to negative infinity. As f of x is going to positive infinity, your x values are going where? Now, what does this mean? Left, right, up, or down? Up. As you go up, where's your graph at? To the left or to the right? It's going to the right. So we're going to say x approaches what? Positive infinity. Now, why does the worksheet give the answers like this? I have no idea, right? Like, I always think of x before thinking of y. So I'm always going to write as x approaches negative infinity, the y's go negative infinity, right? I always talk about x's first. But I just wanted to throw that out there to you because I believe even on the final exam at the end of the semester, they write it like this with talking about f of x and then x second. I don't know why. Anyway, these are already things or statements that we already demonstrated on Desmos with the pictures that I showed you. It says if your polynomial function has an even degree, then the end behavior will be in the same direction. So if you have an even degree, all these are even degrees. You have the y equals x to the power of 2, x to the power of 4, x to the power of 6. Where are all these end behaviors at? What quadrants? First and second. So it's going to be up here somewhere and up here somewhere, right? Now, of course, if you were to put like y equals x to the 6th plus 5x or plus x to the 5th, take away 7x to the 4th plus 4x to the 3rd, and so on down to your constant, then some other things are going to be happening right here, but it's still going to have the same end behavior. Likewise, if you were to take those even degree functions and put a negative leading coefficient in front of all of them, where's your end behavior going to be at? Third and fourth. Okay, it's going to be down here and down there, right? I mean, who knows what actually happens right here in the middle? It could be going up, down, up, like that. Who knows, right? We'll talk about the middle later on next week. Right now, we just want to talk about end behavior. What about if you have an odd degree function? And there was a typo right here. This should have been a 7. Sorry. But if I have all these odd degree functions, y equals x to the 3rd, y equals x to the 5th, y equals x to the 7th, where's the end behavior going to be at? What quadrants? First and third. That's right. Up here and down here somewhere, right? Who knows? Maybe it goes up, down, up, like that. Who knows, right? And that all depends on your degree. Obviously, this is going to be a pretty high degree with a bunch of other stuff, like maybe like y equals x to the 7th plus x to the 6th, take away x to the 5th, minus 4x to the 4th. I don't know, right? But other things will happen in the middle, but the end behavior will be the same. Now, if you were to reflect with the negative as your leading coefficient on any odd degree function, where would you end up? End behavior. Second and fourth. Second and fourth. So you're going to have end behavior up here and down there. And of course, who knows, if you have like a y equals negative x to the 7th plus x to the 6th minus x to the 5th plus x to the 4th, you might end up with like some weird, really weird looking curves like that, right? Anyway, final detail. Remember, if they ask you for the real zeros when they give you a graph, what they're simply asking for are the x-intercepts. Real zeros are x-intercepts. X-intercepts are real zeros. I mean, they're also technically called roots, solutions, answers. But if I were to give you that exact graph right there and I said, how many real zeros does it have? What would you say? It actually has 1, 2, 3, 4, 5. That's right, 5 real zeros. Okay, so that's important. We're supposed to practice from the book. I know you guys don't have books, so that's why I took a picture of the book. I would like you to try 35 through 40. And it's really simple. They ask 3 things for each graph. Describe the end behavior. Part B, determine whether it represents an odd or even degree function. And part C, state the number of real zeros. So let's begin with describing the end behavior. What are we going to write? As x approaches negative infinity, that's saying as it goes to the left, your y values go where? They go up, positive infinity. Okay? And as x approaches positive infinity, let's look at to the right, where do your y values go? They go also to positive infinity. Super easy. You guys got it. That is function, that's what is that? End behavior notation, right? Is this an odd degree function or an even degree function? Even degree function. So that's part 2. Even degree function. And you know what? We could even take it a step further. Is the a value, is the leading coefficient on your even degree function positive or negative? It's positive because we know that it's opening up here and up there. If the leading coefficient were negative and it were even, it'd be down here, right? So that's good to know. And last but not least, how many real zeros do I have? 4. 1, 2, 3, 4. Perfect. And that's it, right? That is it. That's the entire lesson. I know it was long, but I hope you guys understand it, because it's really not about doing math. It's just about understanding it, right? There are other questions on this homework assignment, and on Google Classroom, I have a video explaining every single one, okay? So if you have any questions, watch those videos, and this will be on the test next week, next Thursday.